In this video, we're going to address three special situations that can arise when solving differential equations using the eigenfunction expansion approach. The first is converting our differential operators into a self-adjoint or Sturm-Liouville form. The second is what happens if we have a non-homogeneous differential equation. And the third is what happens if our boundary conditions are non-homogeneous. So let's take a look at those three special situations here. So not all second-order linear differential equations are in the self-adjoint Sturm-Liouville form. So for example, if you take the Chebyshev equation that we had in the previous video and simply rewrite it by multiplying through by some factor to get this form is not in self-adjoint or Sturm-Liouville form. We have to multiply times this 1 over the square root of 1 minus x squared in order to put it into that self-adjoint form. So it turns out that any second-order linear differential equation can be put into a self-adjoint form, and we want to show how that's done here. So let's take a general second-order linear ODE, a0 times the second derivative plus a1 times the first derivative plus a2 times u, and then this is a differential eigenproblem, so there's a lambda times a3 times u as well. The a0, a1, a2, and a3 can, in general, be anything. And we want to determine how to convert that into the Sturm-Liouville self-adjoint form. To do that, let's divide through by a0. So that way there's just a coefficient of 1 on the second derivative, and then a1 over a0, a2 over a0, and a3 over a0. Likewise, let's take the Sturm-Liouville form, expanding that first term out using the product rule to get these two terms, p times the second derivative plus dp dx times the first derivative, and then this is unchanged here. Now let's divide through by p so that the second derivative term also has the coefficient 1, so that's 1 over p times dp dx, q over p, and w over p. So if we want these two equations to be the same, well, 1 and 1 are already the same. a1 over a0 would have to be equal to dp dx over p, so that'll be our first requirement. And then a2 over a0 would have to be equal to q over p. That would be our second requirement. And a3 over a0 would have to be w over p. That's our third requirement. So let's take a look at this first one. And we're going to integrate both sides with respect to x. So if the integral of p prime over p, well, that's just the natural log of p, is then equal to the integral of a1 over a0. So that's what we have here. To get rid of the natural log, we can take the exponential of both sides. So we have p times the exponential of the integral of a1 over a0. So that gives us an expression for the function p in terms of the a0 and a1 coefficients in the original second-order linear ordinary differential equation. Once we have p, if you look back here, that gives us these. We can solve for q and w. Q is just a2 over a0 times p, and w is just a3 over a0 times p. So in that way, we can get the p, the q, and the w being the weight function, in our Sturm-Liouville form. And that gives us our self-adjoint form. And that's actually how we determine that weight function, w of x. In the past, I've kind of left that somewhat nebulous. It's probably been a bit confusing, but that's in fact how you get the w. It comes from right here. Okay, the second eventuality is what happens if we have a non-homogeneous equation. So we have a forcing term on the right-hand side of our equation. We actually did an example of this earlier in section 3.2, and we did that by expanding both the solution, u of x, as well as the right-hand side function, f of x, as a linear combination of the eigenfunctions of the differential operator. So we did that in that example. Here I just want to do the same thing, but in a more general way, for any f of x. So we write the f of x as a linear combination of the eigenfunctions, the u sub n's. So the a sub n hats are the unknown coefficients. The way we get those is to simply take the inner product of each eigenfunction, u1, u2, u3, through u infinity, with our f of x. And you take that inner product, and that's going to give us those coefficients. So when we take that inner product, f is an infinite series expansion, has an infinity of terms. However, you notice each term has one of the eigenfunctions in that term. So when you take the inner product with um is going to be u0 or u1 or u2 or u3. All of the other terms other than the mth term is going to vanish because the inner product of each eigenfunction, which each of the other eigenfunctions is going to vanish, is going to be 0 because they're orthogonal. So the only term from this infinite summation is going to be the term corresponding to the u sub m that we took the inner product with. So in that way, all of these terms go away except for that one term. So we then have the inner product of u sub m with f of x, always with respect to the weight function, is equal to a sub n hat, those are the coefficients that we're looking for, times the integral of um with um. That's the inner product of um with itself, so um squared, again with respect to its weight function. Well, this is simply the square of the norm of our eigenfunction u sub m. And then on the left-hand side, that's the inner product of u sub m with f of x. So the coefficient that we're looking for, a sub m or a sub n, doesn't matter which, a sub n hat is simply then inner product of um with f of x over the square of the norm of un. And if you look back in our earlier examples, this is exactly what we did in those cases as well. This is just the general form of it. Now you'll notice if we've already normalized our eigenfunctions so that their norm is 1, then this denominator will simply be 1. And the coefficients then will just be the projection of the f of x on each of the corresponding eigenfunctions u sub n. And you'll notice even if we look back in chapter 2, equation 2.7 to be specific, this is perfectly analogous to the same situation that arose solving systems of linear algebraic equations au is equal to b, where the right-hand side vector b is like our right-hand side function f of x. Okay, now let's look at our third eventuality, and that's when we have non-homogeneous boundary conditions. Remember, in these eigenfunction expansion problems, we've been saying that the boundary conditions have to be homogeneous. And the reason for that is because we apply integration by parts in order to get the adjoint of a differential operator. In order for the terms at the boundaries that arise from the integration by parts to vanish, the boundary conditions have to be homogeneous. What if the problem that we're given has non-homogeneous boundary conditions? What do? Well, we have to do a change of variables. We have to do a transformation in order to move the non-homogeneity from the boundary conditions onto the equation itself. So let's show how to do that. We'll do an example. So let's say we have d squared u dx squared plus the quantity 1 plus x times du dx plus u is equal to 0. So that's a homogeneous second-order linear ordinary differential equation. The boundary conditions are u at 0 is 0, which is homogeneous, and u at x is equal to 1 is 1, which of course is non-homogeneous. So what we want to do is come up with a new variable, we'll call it capital U, such that in terms of capital U, the boundary conditions are both homogeneous. In doing so, it's going to move the non-homogeneity from the boundary condition to the equation itself, as you'll see. So here's the basic process. So we have our original variable u of x. We're going to say that's equal to phi 0 of x plus capital U of x. Capital U of x is going to be our new dependent variable. Then phi 0 of x is going to be a function specified by us that takes into account that non-homogeneity in the boundary conditions. So here's how that works. So we look at our boundary conditions and we ask ourselves, what's the simplest function, phi 0 of x, that would satisfy these boundary conditions such that the capital U of x can be homogeneous on both ends of the domain? Well, the simplest in this case would simply be phi 0 of x is equal to x. That would be a straight line between 0 and 1 at x is equal to 1. It's the simplest function that satisfies the boundary conditions and renders them homogeneous in the new variable. So if I set phi 0 is equal to x and do the transformation, so u is equal to x plus capital U of x. If I plug that in for u everywhere in the equation and in the boundary conditions, we'll get a differential equation now for capital U. So d squared u dx squared plus 1 plus x times du dx plus u is equal now to minus the quantity 1 plus 2x. So the first thing you'll notice, it's still second order, it's still linear, so it's of the same form as the original differential equation, but it's slightly different, and it now has a non-homogeneous right-hand side. So we now have an f of x. But in terms of the new variable, capital U, you'll notice that both boundary conditions are now homogeneous. So now we could use the method we just discussed a moment ago to handle this non-homogeneity in the differential equation itself, but we can use the eigenfunction expansion approach because we now have homogeneous boundary conditions. Now, as always, this equation in this particular form may or may not be self-adjoint. So you may have to use the other approach that we discussed at the beginning of this video to convert this differential equation into an equivalent Sturm-Liouville form.